Hello again and welcome back to your favorite family show, Memflow Applied. It's your host, me, and I'm back with something absolutely incredible. I've got a gift, a Christmas present. It's something that will make our scans absolutely incredibly fast, rapid, instant, amazing. What is it, your question is, and the answer to it is, well, it's an optimization that essentially flips everything upside down. It flips all the scans upside down and makes us scan in reverse. And when we scan in reverse, we can do it much, much faster. But before that, I'll just show you what we have for now. Our usual offset scanner, which it does scan stuff. Let's actually time how long it takes to run it. For that, we're gonna use, well, timer. And that will be start equals instant now. And the instant is going to be instant right here. And we just do this thing called matches found in 0.2 milliseconds. So that will be start.elapsed.as seconds f64 multiply by 1000 to convert seconds to milliseconds. If matches dot length more than 128, printing first 128 matches. And we need to just take 128 matches or 64, just so that we don't overflow with millions of matches. Now, at this point, when we run it, we run offset scan yes 0.32.5, and it takes 300 milliseconds because the first time it initializes the global variables and offsets. It's instant, actually, when you run it the second time. But if you go offset scan yes, increase the range to 256 and set the depth to 6. As you can see, it takes 2 seconds. But now, if we increase the depth to 7, well, it's gonna take a while. And why don't we just cut? We did it. But how long it took? Well, it took 29 seconds. And that's not cool. That's not cool. That is incredibly slow. We can do much, much better. 29 seconds for 21,000 matches, that is unacceptable. You think it's acceptable, but I'm gonna show you something much, much better. And well, let's just check it out, shall we? Don't forget to overflow that like button. This is the like button, overflow it, it helps me tremendously. Thank you very much. What we're gonna do, we're gonna create a inverse map so that we can scan things in reverse. As you can see, the map right here, it maps a pointer to its ending address. And you can have multiple pointers mapping to the same single address. In reverse map, you would have a inverse map, which is the same B-tree map, and it points an address to a multiple starting addresses. So that would be a vector of addresses. And we will also need a vector of these starting addresses for scanning purposes later on. I will show you what that means. So it will be pointers. It will just be a vector of addresses. And now the reset function is going to just clear all these three things. Self.inverse map dot clear, self.pointers dot clear. And right now in the create map, we actually want to reset it beforehand, so it will be self.reset, because we don't want to add duplicates on top. We don't want to print stuff anymore because this can be a library, this will be a library, and we don't want to have like leftover print statements, so we remove that. And it will be rather simple, I'd say. It will be just for key and value in self.map. We just do self.inverse map. We need to push the key, which is the starting address, to the value, which is our ending address. So it will be self.inverse map dot entry. Entry we pass in the value as our key. And mind you, this value might not exist yet, so we need to insert an empty vector if it's empty. So we will use our default, which right here, it ensures the value is in the entry by inserting a default value if empty. And it returns, well, mutable reference to the vector we need. So it will be just push on top, we push the key. And now to create the pointers, it will be, well, self.inverse map dot keys dot copy dot collect, and that will be it. We actually go through map dot keys and collect them. Now we just create the getter methods for these two things. So it will be self.inverse map. It will return a B-tree map of address to a vector of addresses, and pointers will be self.pointers right here, and this is inverse map. And once that's done, it claims that this function is unused. Let's fix that, because this will be a library, so we're just gonna, well, mark these modules as public. All of the modules as public. Now we need the same thing for the disassembler. We need the same access to the global variables. So we will create the same, well, map. So we copy these. We pass these through. We also pass this through right here. We remove the print statement. We add a reset call right here. We paste this in. We paste this in, except instead of pointers, it's globals. So globals. And here we go. Now we've got our boilerplate set up. But what we're gonna do now, we're going into the meat of this episode, and that is the search. The search by itself is essentially inverted. Instead of starting at the entry points, at the global variables, and walking downwards to the matches, we flip it upside down and we start from the matches and we walk upwards towards our global variables. So everything needs to be inverted. For instance, find matches. Right now, the addresses is the global variables, and we go through them multiple times. So it can't be an iterator. It has to be, well, it has to be a slice of addresses. Meanwhile, search for, well, we go through them only once. We will go through them only once, so it becomes an iterator. Item equals address. And we just delete this whole thing. So now, in the for loop, we go through the match in search for, and the addresses, well, let's give it a proper name. It will be entry points. We go through them, and we start at that match, right? We pass, not search for, we pass entry points. And that's roughly it. We just need to update this thing to have implement iterator item equals address. And right here, we pass in self.pointers. It's our, of course, pointers that we defined earlier. And now we need to actually go through our walk down range. So instead of search for, it will be called, well, start points. And now we need to do everything in reverse. That means the min-max bounds, they need to swap upper range and lower range because we start from the endpoint. If we take 0 to 32 range and scan forwards, in the backwards, we need to subtract that 32, so it has to become 32 to 0 range. Now let's fix up this max levels thing. Right here we recurse downwards if possible. So it will be, well, we pass start points right here. Make sure the difference is inverse as usual. We push this address and offset. We don't push the address. We instead push the key. And we go through inverse map, of course. So this will be a vec instead of v. And we go from for each v inside the vec. So it will be this. We go through each v inside the vec, and we push the key and offset pair on the stack, and then we push that new address which we found. And we have the same thing, start points out temporary, and that works. Now we need to add another thing, and that is, well, search for. We actually go through start points. But you see, we could go and filter them out like so, but we can have quite a lot of start points, so we can't quite do that. We will do a binary search because, well, these start points are assumed to be sorted, are always assumed to be sorted. Find the lower bound. So that will be start points, binary search, not by. We just search for, well, our minimum. And if it doesn't work, we unwrap. Well, we don't care whether we have the exact match, so we just find the lower bound like so. Unwrap or else. Yeah. And now we create an iterator. Iterator would be start points dot iterator. We need to skip the previous indices, copy the values. So take while v is less than maximum bound, the upper bound. And once we have that, we just go for entry within the iterator, and we just calculate. We just do the same thing right here. Push matches if found. Of course, the address and m needs to be address and e. It's not the match we've got right here. Now, the temporary vector, as it is reversed, it starts from the match outwards, but we need to push the correct order, so we need to actually, well, reverse it. Remember, everything is reversed, and once it's reversed, you need to just push it on the final output. However, there's a bit of an issue. This thing right here is wrong, because this will be, the E will be one of the start points. If you recall what we had right here, it's actually the match, the final address which we get to. And we need to know it so that we can get it. So what would it be? Well, it would be something like, I don't know, final address. And we don't have it, so we need to pass it through. So I think it's fair to pass it through the temporary variable. So final address, and it will be a tuple, well, address, and we need to, well, pass in final address like so. And there are quite a few issues with this whole thing. There are too many arguments, so it will be, let's unify these things so that there are not too many arguments. So max levels, level. So we pass through upper range. Range, it's usize, and usize, don't care about range here. range is a tuple of usize, right like so right here. And once you have that covered, in the main function, we need to pass the correct, well, arguments. So it will be this changes, but we need to, well, pass through. The matches need to be iter.copied. The matches need to be copied, just like so right here. And we need to change this into a slice. So now at this point, we don't use this as a map values copied, right? Well, we actually just use disasm.globals, and we don't use the bit reset. That's it, I think. Oh, we need to change this to pass through the match. I had a little bug right here where I needed to also change it to E instead of address. But other than that, it's actually working. For instance, off the scan, yes, 128, 128.7, it calculates it instantly, gets 4,000 matches the way it actually is. Off the scan, yes, 128, 128, 8, we get 21,000 matches in 7 milliseconds. The match count changed a little bit since the start because some pages were paged in and paged out, so I checked, it actually works the same way. Right here, 4K matches in 600 milliseconds, 21K matches in 6.5 seconds that time around, which was really weird. Why was it so fast? But if we go off the scan, yes, 128, this time it's instant in 6 milliseconds, and we can go even deeper. We can go for the scans. Off the scan, yes, 128, depth of 9. And it's near instant 46 milliseconds. Offset scan, yes, 128, 11. Okay, but this time around it's taking a little while, because we picked depth 11, not 10. But this took 7 seconds. And we got 7 million matches. It's incredible. It's absolutely incredible. Another benefit of what we currently have is that we can filter out the matches very nicely. For instance, Office Kanyas 032 5, you've got these 3 matches, and you can also have a negative range. You've got 4 matches and stuff. This is essentially the lowest match. The lowest match is the closest to the pointer. But these, for instance, 4F8030 is absolutely useless, because we've got 4F8040, which is closer than 4F8038, 4F8030. We can really easily filter it out by creating a letmut match m equals none, and by iterating through the matches for E in iter, first figure out the offset. Well, actually, this is iter.next, right like so, and we iterate through, well, address and E, and take the absolute value. Basically, what we can do right now is go through all these matches. As you can see, it starts from the highest one and it goes downwards, right? Because that's the way the matches are structured. And by just, taking the one that's closest to the match we want. So it will be if offset is less than the difference of address to m.unwrap, absolute value of it, we just set that match equals sum e. And we just go if let sum e equals m, we push it in. And what happens right here, this is very, very interesting. pick next match, go through the rest. If app's offset is smaller, override, but also less, instead of less and equals, biases more towards positive. It does because we start from the lower address and the offsets are reversed. So it biases towards more positive end. That means if you have offsets -8 and 8, it's gonna prefer the 8 offset. And it will be, well, much better, I think. That's essentially the gist of it. Push, match, if found. And this is incredibly cool. And we can only do this because we flipped everything upside down and we go through each individual match once. So this way, if we I64 94, if we find actually just one match, which is really cool, which means we can immediately go scan for offsets. We scan 032.5 and you get this single match, which is 4F8040. This is the match we're looking for. And if we go offset scan, yes, 32.5, well, you get the negative offset because, well, it's -8. It's closer to 4F8050 than 4F8040 is. It's closer, so it picks that one up. But if this was -16, if it was 4F80, 60, it would pick 4F8040 first. I hope you get what I mean. But essentially, now this time round, 032.5, we get only the one single match we want. And well, you actually have more matches if you go 128, 128, 5. You've got quite a few more matches. For instance, right here, you can go like 0 to those different offsets. And it finds eventually the match. And you can have 512, which is a 1 kilobyte range, and take depth 8, and it's taking a while, but I'm sure it will calculate it instantly. Here we go. It did it. It took just 4 seconds and it found tremendous amount of matches. It's 4 million, 4.8 million. It's incredible. And we did it in this episode. I will recap real quick. So, what we did in this episode, we added some time calculation, and we actually need to remove the beat reset because we don't use it anymore. So in this episode, what we did was, well, first time how much it takes to run our code. And beforehand, scanning the 256 byte range at the depth of 8 would take roughly 30 seconds, or sometimes for some reason 7 seconds. But it's really, really long. In this episode, what we did, we flipped everything upside down. And we made scans go from the matches outwards. And that made them run at the same depth, at the same range, in less than a second, in less than 10 milliseconds. That's how long it took. That's how short it took to find the matches. And it found the exact same number of matches. And how we did it? Well, we created a so-called inverse map right here and the pointers, which are, well, our matches. And what that let us do is then go and rewrite the walk down range function to have it absolutely reversed. The ranges are swapped, the offsets are swapped, everything is swapped around, and even the clone thing is built in reverse, and then we just reverse it back to the proper order and push it back. And this allows us to add another really cool optimization, which is picking the closest match. We always know that the final address is always the same within the single call to walk down range. That way, if we have multiple global variables within range of the pointer, we can just pick the closest one and thus get the closest match we want, ignoring the global variables around that. This allows us to find the exact match we want. And essentially, this is it. We actually wrapped range into a tuple so that it doesn't complain very badly, but this is what we did. And the result, as I said, is incredible. Incredible performance gains with no downsides, only upsides. Now, thank you very much for watching this episode. In the next episode, we will do quite a lot of quality of life improvements. We will make the tool usable. We will make it actually like write to right values. We will override values. We will add like all the customization for like all the parsing, all the different types of integers to be parsed. And it will be beautiful and it will make the tool really, really usable. So yeah, thank you very much for watching. Don't forget to like this video, overflow it, share it with your friends who you think might find it useful. And yeah, mine was Heap, yours was Undefined. See ya.